Welcome to the Cabinet of Science and Fiction.
And welcome back to you, the learner. Today we're tackling something huge, something that sits right at the heart of what we are and what we might become. We're looking at the dawn of the post-human age.
It sounds almost like science fiction, doesn't it?
Yeah.
But this isn't just speculation anymore. We are right in the thick of a massive scientific revolution.
Exactly. We're talking biomedical breakthroughs, genetic editing tools that let us rewrite our own code, cybernetics blurring the line between us and machines. It's all happening now.
And the potential outcome. A fundamental shift, maybe even a leap, towards what philosophers are starting to call a post-human state. It's a bit unsettling, honestly.
It is. And that's our mission today for you, the learner. We need to dig into all of this. We'll be weaving together scientific research, some pretty deep philosophical arguments, and even warnings from literature.
Right, trying to grasp the practical side, the ethical minefields, and, well, the big existential question. What does all this do to our identity? What does it mean to be human anymore?
We're drawing from a few key areas to guide us. First, there's that core philosophical clash, isn't there? The whole transhumanism versus bioconservatism debate.
Yeah, and we'll look at how classic literature, like Aldous Huxley's Brave New World or Margaret Atwood's Oryx and Crake, kind of sounded the alarm bells decades ago. They saw something coming.
They really did. Then we'll pivot to the really cutting-edge stuff, the concrete technical challenges, and frankly, the ethical nightmares posed by tools like CRISPR-Cas9. The ability to edit our genes, specifically the germline.
That's the one that affects future generations, right?
Yep.
Huge implications there.
Absolutely huge. And finally, we'll explore the philosophical fallout from physical augmentation. Think cybernetics, neuroprosthetics, implants directly interacting with our brains, and even the wild idea of 3D bioprinting organs on demand.
So implants changing how we think, how we feel.
Yeah.
How does that not mess with our sense of self?
That's the million-dollar question, isn't it? Are we heading towards a future of unprecedented human flourishing, better health, longer lives, enhanced minds? Or are we inadvertently designing the perfect cage, a high-tech dystopia?
Let's try and unpack it. Where do we even start? Maybe with the basics, what we traditionally thought human meant.
Good idea. Let's set the baseline before we talk about moving beyond it.
Okay, so before post-human, there was just human. What's the traditional idea we're supposedly moving away from? The humanist ideal, right?
Exactly. This idea really took shape during the Enlightenment with thinkers like Rousseau and Kant. It places the human subject right at the center of everything.
Central because.
Yeah.
What makes us so special in that view?
Well, primarily it's about reason, autonomy, and our capacity for moral judgment. The humanist view sees us as rational agents, capable of making our own choices, understanding the world logically.
Like Protagoras said, man is the measure of all things. We're the benchmark.
Precisely. It emphasizes our uniqueness, our separateness from, say, animals or machines. And this ideal is deeply embedded in things like the Universal Declaration of Human Rights, the idea that all humans possess inherent dignity and rights based on this shared, rational, moral nature.
So we're defined by our minds, our ability to choose freely, our moral compass. That's the stable ground.
That's the traditional foundation, yes.
So then what exactly does posthumanity mean? How does it propose to, well, overcome that?
Posthumanity signifies moving beyond the merely human, displacing that anthropocentric view. It's not about seeing humans as the pinnacle anymore.
So less focus on our special uniqueness.
Right. It embraces hybridization, mixing human with technology or altering biology. It talks about heterogeneity, multiplicity. The posthuman isn't necessarily a single, stable, autonomous entity in the same way.
It sounds like blurring the lines we thought were so clear between human and machine, human and modified human.
Exactly. It's about potentially transcending the biological and cognitive limits we currently take for granted. And thinkers like Nick Bostrom have actually tried to quantify this.
Quantify post-humanity. How?
Well, Bostrom laid out some pretty specific, almost startling criteria for what a post-human condition might look like. It's not just about minor improvements.
Okay, like what? Give me some examples.
For instance, population size. He suggests a post-human civilization might number over 1 trillion individuals, maybe spread across different planets or habitats.
1 trillion. Wow. Okay, that's vast. What else?
life expectancy, not just adding a few years, but potentially living over 500 years on average.
500 years. Imagine the social implications of that. Careers, relationships, family structures, everything changes.
Completely reshaped. And then there's the cognitive aspect, which is maybe the most radical.
More radical than living for 5 centuries.
I think so. Bostrom talks about cognitive capacities potentially being twice the current human maximum, not just raising the average, but doubling the abilities of the most brilliant minds alive today.
So, superintelligence, essentially, operating on a totally different level of thought.
That's the idea. And it extends to emotional and sensory control, too. Near total control over sensory input, and maybe even the extinction of psychological suffering.
Eliminating suffering. That sounds good on the surface, but also kind of scary. Like removing a fundamental part of the human experience.
That's the heart of the debate, isn't it? For transhumanists like Bostrom, things like aging, cognitive limits, even suffering, aren't sacred parts of being human. They're biological limitations, evolutionary baggage.
Just problems to be solved with technology.
Essentially, yes. They see human nature not as a finished product, but as Bostrom put it, a work in progress, maybe even a half-cooked beginning. The goal is to use reason and technology to consciously redesign ourselves to transcend those limits.
So it's intentional self-evolution.
That's a good way to put it. But this whole way of thinking, this possibility, didn't just appear out of nowhere. It was really enabled by a couple of major scientific shifts in the mid-20th century.
Okay, what were they?
The first big one was the cybernetic revolution, starting around the 1950s, 1960s.
Cybernetics. That's about systems control, feedback loops, right? How did that change how we saw ourselves?
It introduced a powerful new language logic, mathematics, information theory to describe living systems, including humans. Suddenly, we started seeing ourselves less as mysterious beings with souls or deep psychological interiors, and more as complex information processing entities.
So like biological computers.
In a way, yes. Thinkers like Catherine Hales argue that information itself became seen as this universal organizing principle, almost replacing the concept of life as the defining characteristic of being. If you can describe a human and an intelligent machine using the same informational terms,
Then the lines blur. The physical body starts to seem less important than the information pattern.
exactly. And this leads to a really crucial concept, the discorporization of reason.
Decorporization, taking reason out of the body.
Precisely. If thinking, memory, consciousness are fundamentally just complex information pattern software, if you will, then maybe that software isn't intrinsically tied to the biological hardware, the body.
So the idea that you could, like, upload your mind.
That's the ultimate fantasy that emerged from this thinking. People like Marvin Minsky seriously explored the idea of extracting human memories, maybe even consciousness itself, and downloading it onto a computer. It suggests a path to effective immortality, escaping the decay of the physical body altogether.
Mind is software, detachable from the meat. Okay, that's one major shift. What was the other one?
The other shift happened almost in parallel, driven by advances in molecular biology and genetics, especially after the Human Genome Project. This is a biotechnologies revolution.
So while one revolution was dematerializing the mind, this one was focusing intensely on the material body.
Exactly. It created immense social pressure to view ourselves as somatic individuals. Our identity became increasingly defined by our biology, our genes, our neurochemistry.
You see this everywhere now, right? Explaining behavior through brain scans, moods through neurotransmitters, potential through genetic screening.
Absolutely. There was a shift away from explaining things through, say, deep psychological narratives towards molecular explanations. This fostered a kind of molecular vision of human identity.
And the danger there is.
The big risk is genetic determinism, the idea that we are just our genes, that our choices, our culture, our personalities are ultimately just outputs of our biological programming.
So the autonomous moral agent of the Enlightenment gets reduced to a biological machine.
That's the concern. It potentially biologizes culture and minimizes the role of free will, experience, and social context. It's a strange paradox. One revolution suggests we can escape the body. The other suggests we are nothing but the body's code.
It's a real tension. And it's this exact, messy, contradictory future that writers like Huxley and Atwood explored so powerfully.
They really did. Their works serve as incredible warnings, almost like philosophical thought experiments played out in fiction. Let's start with Huxley's Brave New World. It's from 1932, but feels disturbingly relevant.
Yeah, the Society of Engineered casts alphas, betas, gammas, deltas, epsilons, all conditioned from birth, or rather from the test tube.
decanted, not born. With mass production principles applied to human reproduction, society is engineered for stability above all else. Family, art, religion, deep personal relationships all eliminated because they cause instability and unhappiness.
And replaced with.
Conditioned pleasure, casual sex, everyone belongs to everyone else, and of course the drug soma, which instantly smooths over any negative feelings.
It sounds efficient and horrifying. But you mentioned Bostrom argues these people aren't really posthuman. Why not?
Bostrom makes a crucial distinction. He argues they are dehumanized, not posthuman. Their capacities are intentionally reduced, stunted. They have normal lifespans, but their intellect, their emotional depth, their moral agency are deliberately suppressed by the conditioning.
So it's the opposite of the transhumanist goal of enhancing capacities.
Exactly. Soma isn't about achieving genuine well-being or self-mastery. It's involuntary chemical control. Bostrom calls it the exact antithesis of the transhumanist proposal. Brave New World isn't a future of transcendence. It's a cautionary tale about control leading to diminished humanity. Engineered subhumanity.
Okay. Now, fast forward about 70 years to Margaret Atwood's Oryx and Crake. This feels much closer to our current genetic revolution.
It really does. Atwood explores the fallout of unchecked genetic engineering through the character Crake, a brilliant but deeply misanthropic scientist.
He creates the Crakers, right? These genetically modified humanoids intended to replace us.
Yes, the prototypes living in their little bubble, designed to be the inheritors of the Earth after Crake unleashes a devastating plague.
And how are they designed? What's different about them?
Crake tried to engineer out all the things he hated about humanity. The Crakers reproduce naturally but have enhanced immune systems. They're programmed to die peacefully at age 30, eliminating old age and fear of death. They're genetically incapable of recognizing race or hierarchy. They have periodic mating cycles signaled by physical changes, removing sexual jealousy and complex courtship. And crucially,
What?
they lack symbolic thought. No art, no metaphors, no religion, no lies, no sense of humor. Crake wanted a peaceful, literal-minded species living in harmony with nature.
But he achieves this through mass extinction, unleashing the VEUR virus hidden in a pleasure pill, Bliss Plus.
Right. The pill promised enhanced libido, wellness, and contraception, but delivered annihilation, leaving only the Crakers and the protagonist, Snowman, who was immune.
And again, like Huxley's Citizens, are the Crakers seen as posthuman?
No, for similar reasons. They are beings with deliberately inferior or at least fundamentally different and limited capacities compared to baseline humans. They lack critical thought, the capacity for deep love or complex desire, the drive for meaning-making. They're simplified.
But here's the interesting twist in both novels, right? The persistence of the unbreakable human element. Despite the conditioning, despite the genetic design, something slips through.
It's fascinating. In Brave New World, you see in characters like Bernard Marx. He resists soma. He craves solitude, real conversation, even negative emotions, just to feel authentic. He wants to be unhappy and me rather than happy and someone else.
And Lenina Crown, who's supposed to be perfectly conditioned, still shows hints of possessiveness and confusion about the enforced promiscuity.
Exactly. Deep-seated human tendencies, the need for authenticity, attachment, meaning seem to push back against the conditioning.
And what about the Crakers? How do they defy their design?
This is maybe even more striking. Crake specifically engineered symbolic thought out of them. Yet, by the end of the book, they start exhibiting rudimentary symbolic behavior.
Yeah.
They begin building crude effigies of snowman, their caretakers. They start developing simple chants, almost like prayers when they want something from him. They are spontaneously, instinctively recreating ritual and maybe even religion, the very things Crake tried to erase from their genetic code.
Wow. So the drive for meaning, for symbolism, might be deeper than just a cultural overlay. Maybe it's biologically inherent.
That seems to be Atwood's implication, that some core aspects of human nature, our need for story, for meaning, for connection beyond the purely physical, are incredibly resilient, maybe even irrepressible.
So the ultimate warning from these literary explorations isn't just don't play God, but maybe be careful what aspects of human you try to engineer away, because you might lose something essential or find it impossible to suppress anyway.
I think that's a key takeaway. The danger lies not just in failure, but potentially in a certain kind of successfully simplifying ourselves into something less. And the tool that brings this possibility into sharp, immediate focus today is CRISPR-Cas9.
Right, from philosophical warnings to a specific, powerful technology that's already here. Let's dive into that.
Okay, so CRISPR-Cas9, this is a technology that really shifted the conversation about genetic editing from maybe someday to, it's here.
Because it's just so much better than previous methods, right?
Right.
More precise, easier to use.
Exactly. It's often described as revolutionary because it's incredibly versatile, relatively low cost compared to older techniques, and researchers can adapt it pretty easily in the lab. It's democratized gene editing in a way.
So remind us, how does it actually work? What are the key parts?
It's actually based on a natural defense mechanism found in bacteria. There are two main components working together. First, you have an enzyme called Cas9. Think of it as a pair of highly precise molecular scissors that can cut DNA.
Okay, scissors. And how do they know where to cut?
That's the second part, the CRISPR component.
Hmm.
This is a small piece of RNA that acts as a guide. Scientists can design this guide RNA to match a specific sequence in the genome they want to target.
So the guide RNA leads the Cas9 scissors right to the specific spot on the DNA.
Precisely. The guide RNA binds to the target DNA sequence, and then the Cas9 enzyme makes the cut. Once the DNA is cut, the cell's natural repair mechanisms kick in. Scientists can then trick those mechanisms into either disabling a faulty gene or inserting a new, desired sequence of DNA.
It sounds incredibly elegant and powerful.
It is. The ability to target specific genes with this level of ease and potential precision is unprecedented.
But there's always a but, isn't there? Especially when we're talking about rewriting the code of life. The scientific community itself calls for a pause, a moratorium, on using this clinically in the human germline. Why? What are the technical challenges?
Despite the elegance, there are some major safety and efficacy concerns that are far from solved. The first big hurdle is just getting the CRISPR system into the target cells reliably and safely. This is the delivery transport problem.
How do they ever do that?
Often, they use modified viruses, viral vectors, to carry the CRISPR machinery into cells. Sometimes they use bacterial plasmids.
Viruses. That sounds risky.
It can be. Using viral vectors carries risks of triggering a harmful immune response in the patient. In some past gene therapy trials using viruses, patients experienced severe side effects, including cancer and, in some tragic cases, even death. Non-viral methods like using ribonucleoproteins or lipid nanoparticles are being developed and look safer, but delivery remains a major challenge.
Okay, so getting it there is tricky. What about once it's there? Does it always cut perfectly?
That's the second major concern. Off-target effects. The guide RNA is designed to be specific, but it's not always perfect. It might bind to sequences of DNA that are similar but not identical to the intended target.
So the scissors cut in the wrong place.
Exactly. The Cas9 enzyme might cut the DNA at unintended locations throughout the genome. These off-target cuts could potentially disrupt important genes, cause mutations, or even lead to cancer down the line. Detecting and predicting all possible off-target effects for any given guide RNA is incredibly difficult. Some studies suggest guide RNAs can tolerate several mismatches and still direct Cas9 to cut.
So you could fix one problem, but accidentally create several new, unpredictable ones. That's terrifying, especially if you're editing an embryo.
Precisely. And there's another layer of complexity.
Mosaicism?
Mosaicism, what's
Right.
that? This happens when the editing process doesn't work uniformly in all the cells it's supposed to target. For instance, if you're editing a very early embryo, some cells might get edited correctly, others might have off-target edits, and some might not get edited at all.
So the resulting organism is a mosaic of edited and unedited cells.
Correct. Early studies on human embryos, like the work reported by Liang and colleagues, found mosaicism occurred in a significant percentage of cases, maybe around 25%. This makes the outcome highly unpredictable. Will the intended therapeutic effect work? Will there be unforeseen consequences from the mix of cells? It's very hard to say.
Delivery issues, off-target cuts, mosaicism, it all adds up to a huge amount of uncertainty, doesn't it?
That's the bottom line, especially for germline editing changes made to sperm, eggs, or embryos that will be passed down through generations. We simply don't know enough about the long-term consequences. How will these edits interact with other genes, with environmental factors, over decades? Across generations, the complexity is immense, and our ability to predict the outcomes is currently very limited. Some researchers emphasize we just can't guarantee safety yet.
Okay, the technical risks are clearly massive, but let's imagine, just for argument's sake, that scientists solve all those problems. Perfect delivery, no off-target effects, no mosaicism. Are we then ethically cleared for germline editing?
Not necessarily. Even with perfect technology, we run into fundamental ethical conflicts, which seem to stem from two core principles about germline editing.
What are those?
First, as we mentioned, these changes are permanent and heritable. Any edit made to the germline doesn't just affect the individual, it affects all their descendants. We would be altering the human gene pool indefinitely. That's an enormous responsibility.
We're making decisions for generations that don't exist yet.
Exactly. And the second principle is the status of the human embryo and the impossibility of informed consent. An embryo cannot consent to having its genome altered in ways that will shape its entire life and the lives of its descendants. This raises profound questions about autonomy and rights.
These seem like the bedrock concerns for the bioconservative opposition, right? People like Francis Fukuyama.
Yes, Fukuyama is perhaps the most prominent voice raising alarms here. His core argument centers on the potential loss of human dignity and the erosion of human nature.
What does he mean by human nature in this context?
He refers to the typical characteristics shared by our species, our general range of cognitive abilities, our emotional makeup, our social tendencies, which he believes form the basis for our shared understanding of rights and moral status.
So, messing with that baseline, that shared nature, is dangerous.
Fukuyama argues it is. He worries that if we start engineering designer babies, making some individuals significantly stronger, smarter, or even immortal, we shatter the very foundation of human equality. How can we maintain the principle of equal dignity if some humans are fundamentally different, perhaps superior by design?
It could lead to a genetic caste system, far more ingrained than any social one. Like Huxley's world, but potentially real.
That's precisely his fear. A future where the enhanced elite look down on the naturals, eroding social cohesion and democratic values.
But the transhumanists, like Bostrom, they push back hard against this, don't they?
They do. Bostrom, for instance, tends to view Fukuyama's concerns as rooted in status quo biases or even irrational fear. He argues that things like better health, enhanced intelligence, or greater emotional control are fundamentally good things, blessings, as he puts it.
So why wouldn't we want more of them?
His argument is that enhancement opens up more possibilities for human flourishing. He acknowledges risks, like increasing social inequality, but sees those as challenges to be managed through careful regulation, public debate, and education, not reasons to ban the technology outright. For transhumanists, the ethical imperative is often seen as pursuing enhancement responsibly.
Respecting individual choice to enhance seems central to their view.
Yes, individual liberty and the right to choose what happens to one's own body, or the body of one's future child, which gets complicated, is a key tenet.
This whole intense debate, the technical risks, the profound ethical conflicts, it all came to a head very suddenly and dramatically in 2018, didn't it? With the He Jiankui incident.
That was the watershed moment.
Yeah.
He Jiankui, a scientist in China, announced he had actually done it. He had used CRISPR to edit the genes of twin girls, aiming to make them resistant to HIV.
And the global scientific community reacted with horror.
Pretty much universal condemnation, not just because he crossed the line into clinical germline editing before any consensus or safety standard was met, but because of how he did it.
What were the specific ethical breaches?
Reports indicate numerous violations. Issues with the informed consent process for the parents, allegations of forged ethical review documents, the lack of transparency, and potentially putting the health of the twins and their future offspring at serious, unknown risk for a questionable therapeutic benefit, especially when safer methods to prevent HIV exist.
It was a demonstration of the worst fears about rogue science and lax regulation.
Absolutely. It showed that the technology was accessible enough and the temptation strong enough that someone would cross the line if robust governance wasn't in place. And that directly led to the strong, unified call for a global moratorium on clinical human germline editing.
A pause, basically. Let's stop and figure this out before anyone else tries this.
Exactly. People like Eric Lander and others argued forcefully for it. The incident spurred a much more intense focus on governance. There had already been consensus statements from major scientific bodies around 2015.
Right, laying out some ground rules.
Yes, generally agreeing on a few key points. This technology has amazing potential, but also extreme risks. Transparency in research is absolutely critical. Public engagement and education are vital. And most importantly, edited embryos should not be used to establish a pregnancy until safety and efficacy are proven and broad societal consensus is reached.
But then there was that influential report from the National Academies, NASEM, in 2017 that seemed to slightly crack the door open.
That report was very carefully worded. It maintained a strong distinction between enhancement, which it opposed, and therapeutic uses. It suggested that germline editing might be permissible in the future, but only for treating serious genetic diseases with no other reasonable options, and only under extremely strict oversight and after extensive public discussion.
So it wasn't a green light, but it wasn't a permanent red light either, at least for therapy.
Some interpreted it that way, suggesting it shifted the debate from if to when and how for therapeutic applications, while still drawing a line at enhancement. But defining that line, what counts as therapy versus enhancement, is incredibly tricky. Is correcting genetic deafness therapy or enhancement? What about predispositions to lower IQ? It's a blurry line.
And how does this play out globally? Is there any kind of unified regulatory landscape?
It's patchy, to say the least. International bodies like UNESCO and the Council of Europe have issued declarations and conventions prohibiting or strictly limiting germline interventions, like the Oviedo Convention. But enforcement relies on national laws.
And national laws vary wildly.
Hugely. You have some countries, like Germany and the UK, though the UK allows research, with outright prohibitions and legal sanctions. Then you have places like the US, where federal funding for clinical germline editing is banned, but private research isn't necessarily illegal, creating a complex and sometimes ambiguous regulatory environment.
What about other approaches?
Some countries might have historically had little specific regulation, creating potential havens for controversial research, though that's changing rapidly after the He Jiankui incident. Others might have non-binding guidelines, like China did initially, which proved insufficient. It's a real mix.
This patchwork regulation seems dangerous, especially with a technology this powerful and global.
It is, and it raises huge questions about policy challenges, particularly around access and justice. If or when therapeutic germline editing becomes safe and available, who gets access?
The wealthy, presumably, at first.
That's the major concern. It could massively exacerbate existing social inequalities, creating a genetic divide between the haves and have-nots. This underscores the need for proactive legislation focused not just on safety, but also on fair distribution and ensuring these technologies don't undermine justice and autonomy.
So what are the practical suggestions for controlling this, assuming it will eventually be used therapeutically?
The consensus seems to be moving towards incredibly strict, multi-layered regulatory guides for research, demanding institutional oversight, proof of safety and benefit, maybe even requiring mechanisms to reverse edits if they go wrong, and extensive testing in animal models across generations.
And for actually using it in people.
That would require approval from regulatory bodies like the FDA or EMA, likely demanding even higher standards for safety and efficacy, plus navigating the impossible issue of informed consent for future generations.
It sounds like an almost impossibly high bar.
It should be, given the stakes. And the issue of justice, ensuring affordability and equitable access if it ever becomes mainstream, needs to be tackled head-on through policy, not just left to the market. This is a global conversation, relevant everywhere the technology exists, demanding strong ethical frameworks and institutional capacity.
Okay, so we've gone deep into editing the genetic blueprint. But that's not the only way technology is merging with the human body. What about augmenting the physical self, adding things in?
Right. Let's shift gears from the invisible code to the tangible body and mind, the realm of the cyborg and the augmented self. So we move from editing genes to physically merging with technology. This brings us squarely into the territory of the cyborg.
The term itself feels very sci-fi, but the reality is becoming increasingly commonplace, isn't it? Defined famously by Donna Haraway as a hybrid of machine and organism.
Exactly. It signifies that blurring boundary where the human being becomes, as Catherine Hales put it, articulated with intelligent machines. The technology isn't just a tool we use, it becomes part of us.
And for transhumanists, this isn't just about fixing problems like a prosthetic limb. It's about actively enhancing beyond normal human limits.
Absolutely. The goal is explicitly to surpass limitations. Think of Kevin Warwick, the researcher who implanted RFID chips and even a neural interface into his own arm. His famous quote really captures it. "I was born human, but this was an accident of fate. I believe it is something we have the power to change."
That's a radical rejection of biological destiny.
It is, and it ties back to what we discussed earlier, this idea that technology isn't just external, it's co-constitutive of who we are becoming. Hales calls it technogenesis. Our technologies shape us as much as we shape them.
Leading to concepts like the mobile technosoma or soma technics, basically saying our self isn't confined to our skin.
Right. rejecting the locationalist error that says the self stops at the boundary of the biological body.
Mm.
If a piece of technology is integral to your functioning, maybe even your thinking, is it not part of you?
And the most profound testing ground for this idea right now seems to be neuroprosthetics, especially implants that interact directly with the brain, cognitive neuronal implants, or ICNs.
Yes, these are devices designed not just to restore lost function like cochlear implants, but potentially to enhance cognitive functions, memory, processing speed, maybe even mood regulation. They're seen as potential upgrades on demand.
But implanting technology directly into the brain, that feels like it strikes right at the core of our identity, doesn't it? More so than a hip replacement.
Absolutely. And this is borne out by experiences reported by patients with brain implants, like those used for deep brain stimulation, DBS, to treat Parkinson's or other conditions. They often experience a profound identity crisis.
What does that crisis look like? Sources mention a specific conflict triad.
Yes, researchers have observed three recurring themes. The first is a crisis of authenticity.
Meaning the implant or its effects feel foreign.
Exactly. Patients might feel the restored function or even a new feeling or thought pattern generated by the implant isn't genuinely theirs. It feels artificial, imposed, like the quote from a heart transplant patient. "The heart beating in my chest is not really mine." There's a sense of estrangement from the technologically mediated function.
Okay, that's authenticity. What's the second conflict?
That's a deeper crisis of identity. Patients might feel they are fundamentally no longer the same person they were before the implant.
Like, I am literally someone else now.
Yes. Quotes like, "My old self has disappeared. I am no longer me. I am another," capture this feeling. The perceived change is so profound, it fractures their sense of continuous selfhood.
That's disturbing.
Uh-huh.
And the third part of the triad.
Alienation. This is the experience of feeling like a machine or being controlled by the technology, losing the sense of authorship over one's own thoughts, feelings, or actions.
Am I choosing to do this, or is the implant making me do it?
Precisely. If your mood suddenly lifts when the device is adjusted or a tremor stops when it's switched on, it can lead to feeling like a puppet controlled by the technology rather than an autonomous agent.
And you mentioned these conflicts seem particularly intense with brain implants, more so than other kinds of transplants or prosthetics.
Yes, because the brain is so intimately tied to our sense of self, our personality, memories, beliefs, emotions. Altering brain function directly impacts the very things we consider constitutive of who we are.
Patients report feeling like their core opinions or personality traits are suddenly fragile, at the mercy of a switch.
That's a common theme. The realization that deeply held beliefs or characteristic moods can be instantly changed by adjusting an electrical current can be incredibly destabilizing to one's sense of a stable, authentic self. It suggests identity might be more fluid and technologically contingent than we like to believe.
This identity crisis is a serious psychological hurdle. How have philosophers tried to address it? I know the extended mind theory, EMT, came up.
Right, EMT, proposed by Andy Clark and David Chalmers, offers a really radical way to potentially dissolve this crisis.
How does it do that?
Their core idea is that the mind isn't necessarily confined to the skull. Cognitive processes can actually extend into the environment. If an external tool like a notebook, a smartphone, or crucially, a neural implant is reliably coupled with your brain and plays a crucial role in your cognitive processes like memory or calculation, then that tool should literally be considered part of your mind.
So the implant isn't an alien intrusion, it's just the new boundary of your extended self.
That's the implication. The cognitive system is the whole loop brain, body, and relevant bits of the world, including technology. So the strangeness or alienation comes from mistakenly thinking your mind should stop at the skull.
Okay, that's a fascinating way to reframe it. But does this EMT view hold up? Our sources seemed critical of its initial formulation.
Yes, critics like Acarte and Garcia Valdecasas argue that the original, strong version of EMT has some problems. They point out its deterministic and locationalist assumptions.
Meaning it assumes mental states are strictly tied to specific physical locations or states.
Kind of. It implies that if you change the physical component, the implant, you necessarily change the mental state in a direct, determined way. This leads to what they call a weak identity, WI view.
Weak identity. Like the ship of Theseus again. If you replace parts, it's not the same thing anymore.
Exactly. If identity is just the sum of its currently configured physical parts, brain plus implant, then changing those parts means you are fundamentally a different person. This view essentially says, yes, you are alienated because you are different now. It validates the patient's crisis rather than resolving it. Clark himself even suggested this means we're all basically cyborgs already, constantly changing as our tools change.
That doesn't sound very helpful for someone struggling with feeling like they've lost their self.
Not really, which is why the alternative, the indeterminist view, IEMT, was proposed as a counter. This view challenges the strict link between mental states and specific physical platforms.
Now,
It draws on the philosophical concept of multiple realizability. This is the idea that the same mental state, say, feeling happy or believing that Paris is the capital of France, could potentially be realized by very different physical states.
so my feeling of happiness could have a different neural pattern today than it did yesterday, or be different from your neural pattern of happiness, but it's still recognizably happiness.
Precisely. The mental content isn't rigidly locked to one specific physical configuration. It's realizable in multiple ways.
And how does that help with the identity crisis?
It suggests that mental life, especially the first-person experience of being me, has a degree of independence from the specific physical hardware. This leads to the idea of a strong identity, SI,
Strong identity
meaning that the core self, the I that experiences, persists even if the physical substrate, the brain, the body, the integrated technology changes. Your fundamental identity as that particular person remains stable, ontologically speaking, even if your functions, memories, or personality are altered by an implant.
So the implant might change how I think or feel or what I remember, but it doesn't change the fundamental fact that it is me who is thinking, feeling, and remembering.
That's the core idea of strong identity. It argues for an irreducibility of the first-person perspective. You remain the same subject of experience, even if the characteristics of that experience are modified by technology.
And this view has a clear ethical advantage for patients, doesn't it?
A huge one. The strong identity view is considered less invasive therapeutically because it aligns with the patient's intuitive sense of self-preservation. It allows them to integrate the functional changes, this implant helps me walk, think, feel better, without feeling like their core self has been annihilated or replaced.
They can see the technology as a tool that assists them, rather than something that turns them into someone or something else.
Exactly. It preserves their sense of agency and continuity, which is crucial for psychological well-being when undergoing such profound bodily modifications. It offers a way to embrace the benefits of augmentation without succumbing to existential dread.
This distinction between weak and strong identity seems crucial as these technologies become more integrated. Okay, so we've covered editing the code and augmenting the existing body-mind. What about creating new biological parts from scratch?
Right, that takes us to our final technological frontier for today, 3D bioprinting. Manufacturing life piece by piece.
So 3D bioprinting. This sounds like something straight out of a futuristic movie, but it's aimed at solving a very real, very current crisis.
Yeah,
right?
Absolutely. The primary driver behind bioprinting research is the desperate organ scarcity crisis.
The numbers are just staggering when you look at them.
Yeah, they really are. Just in the U.S., there are consistently over 100,000 people on the official waiting list for an organ transplant, sometimes closer to 110,000.
And the number of transplants performed each year.
It's only around 40,000. That gap means that, on average, about 17 people die every single day in the U.S. alone while waiting for a life-saving organ. It's a massive unmet medical need.
A silent epidemic, almost. Yeah. And 3D bioprinting offers a potential way out.
That's the hope. The ultimate goal is to use 3D printing technology to create custom-made, fully functional, biologically compatible organs using a patient's own cells. It falls under the umbrella of regenerative medicine.
Using the patient's own cells. That seems key.
It's crucial. We'll come back to why in a moment. But first, how does it even work? How do you print an organ?
Yeah, it boggles the mind. You can't just use plastic filament like in a regular 3D printer.
Definitely not. The process relies on specialized materials called biotinks. These aren't plastics. They are complex mixtures containing living cells, often stem cells derived from the patient, along with biomolecules like growth factors and scaffold materials, often hydrogels, that provide structure.
So the ink is actually alive?
Essentially, yes. This biotink is then loaded into a specialized bioprinter. There are different methods used to deposit the biotink layer by layer, building up the complex 3D structure of the desired tissue or organ. Common methods include extrusion-based printing, kind of like squeezing toothpaste through a nozzle, droplet-based, like an inkjet printer, and laser-assisted methods for higher precision.
The challenge must be keeping the cells alive and getting them to organize correctly, form blood vessels, etc.
That's the core difficulty. Ensuring the printed construct gets nutrients and oxygen, develops functional vasculature, and matures into working tissue is incredibly complex. But there are constant advancements.
Like the work mentioned from the University of Virginia.
Right. They've been developing a method called DATS-P, digital assembly of spherical particles. They use special hydrogel biotinks designed to mimic the properties of human tissue, and crucially, they've found ways to rapidly bond these printed structures together, sometimes in under a minute. This speed could be vital for creating larger, more complex tissues before the cells start to die.
What kind of progress have we seen so far? Have they printed anything complex yet?
We're not printing full hearts or kidneys for transplants just yet, but the progress is significant. Tissue engineers using 3D bioprinting have already successfully created simpler tissues like skin grafts, bone structures, cartilage, muscle tissue, and even blood vessels in the lab. These are being tested for therapeutic uses. The next big leap is scaling up to solid, complex organs.
Okay, let's assume they achieve that. What are the major benefits compared to traditional organ transplants? You mentioned using the patient's own cells.
That leads to the single biggest advantage: eliminating rejection. Because the organ is built from the patient's own cells, autologous cells, their immune system recognizes it as self. It doesn't mount an attack like it often does against a donated organ from another person.
Which means no need for immunosuppressant drugs.
Exactly. Patients receiving traditional transplants have to take powerful immunosuppressive drugs for the rest of their lives to prevent rejection. These drugs have serious side effects, increased risk of infections, cancers, kidney damage, etc. Bioprinted organs from a patient's own cells could potentially eliminate the need for this lifelong medication, leading to much better long-term health outcomes and quality of life.
That's a massive benefit. What about the economic implications? This sounds incredibly expensive to develop.
The upfront R&D costs are enormous, no question, and the initial procedures will likely be very expensive. However, the long-term economic argument is actually quite compelling.
How so?
Think about the ongoing costs of traditional transplants. A kidney transplant can cost upwards of $400,000 initially, plus tens of thousands of dollars every year for immunosuppressants, monitoring, and treating complications. If bioprinting offers a one-time solution that avoids lifelong medication and reduces the risk of organ failure, the total lifetime cost could actually be significantly lower. Estimates suggest potential long-term savings of 25–50% compared to the current system.
So a higher upfront cost for potentially much better outcomes and lower long-term costs. Makes sense. But, like everything else we've discussed, there must be significant ethical and regulatory barriers.
Absolutely. The first major hurdle is simply getting these therapies approved for human use. The FDA approval path, or equivalent bodies elsewhere, is incredibly rigorous and long.
What does that involve?
Years, likely decades, of meticulous work. Extensive preclinical studies in labs and animals to prove safety and efficacy. Then, filing an investigational new drug IND application, followed by multi-phase clinical trials in humans, phase 1 for safety, phase 2 for efficacy, phase 3 for large-scale confirmation. They need to demonstrate not just that the printed organ is safe, but that it's durable and functions just as well as or better than a donated organ. It's a massive undertaking.
So widespread clinical use is still quite a way off.
Likely a decade or more for complex organs, realistically. But beyond the regulatory path, bioprinting raises its own set of new ethical concerns, distinct from genetic editing or neuroimplants.
Such as?
One major area is animal rights. Currently, perfecting biotinks and scaffolding often involves materials derived from animals, or research exploring xenotransplantation growing human organs in animals like pigs. This immediately brings up ethical questions about animal welfare, the conditions they're kept in, and whether it's justifiable to use animals as bioreactors for human parts.
That's a tough one. Using animals to save human lives. Where do you draw the line?
It requires really strict ethical oversight, ensuring humane treatment and minimizing suffering. But it's a debate society needs to have.
And what's the other major concern?
Closely related is the zoonotic disease risk. Whenever you use animal cells or tissues, or even materials derived from them, there's a potential risk of transmitting animal diseases, viruses, bacteria, prions to human recipients.
Like concerns around pig viruses if you use pig scaffolds or cells.
Exactly. This requires incredibly stringent screening, sterilization, and ongoing surveillance to prevent novel pathogens from jumping the species barrier via these medical technologies. It adds another layer of complexity and risk that needs careful management.
Wow, so even this seemingly straightforward solution of printing spare parts comes loaded with its own ethical baggage and technical hurdles.
Nothing in this post-human frontier is simple, it seems. Every advance opens up a new set of complex questions. Hashtag, tag outro.
We've covered a huge amount of ground today. From the philosophical anxieties about changing human nature, going back to Huxley and Fukuyama, all the way to the nitty-gritty of CRISPR gene editing.
And the identity crises sparked by brain implants, and now the potential and perils of manufacturing organs with bioprinting. It really feels like we're standing at a crossroads.
It does. Humanity has developed tools that allow for something unprecedented: intentional self-directed evolution. We can now consciously choose to alter our biology in ways that were previously unimaginable.
And as we've discussed, this knowledge, this capability, we can't really unlearn it. The genie is out of the bottle. So the key challenge moving forward isn't just technical, can we do this? It's fundamentally moral and regulatory. Should we do this? And if so, how?
The warnings from literature seem clear. Unchecked power, whether wielded by a controlling state like Huxley's or a misguided individual like Atwood's Craik, can lead to dystopian outcomes, erasing essential parts of humanity.
Which means protecting individual liberties, ensuring democratic oversight, fostering broad public debate, and building robust ethical frameworks is absolutely paramount. We need to prevent these powerful technologies from creating new forms of discrimination or reinforcing old inequalities.
That concept of strong identity, SI, we discussed earlier, seems particularly relevant here, doesn't it? If we accept that our core self, our fundamental personhood, isn't reducible to just our genes or our physical parts,
Then it provides a kind of stable ethical anchor, perhaps. It suggests that even with significant biological or technological modification, the individual retains their inherent worth and dignity. They are still them.
But here's the final provocative thought, the tension that remains. If strong identity reassures us of our inherent worth, regardless of modification, how do we balance that with the undeniable ethical pull to use these technologies? The functional imperative to alleviate suffering is incredibly strong.
Right. How do we weigh the preservation of a familiar sense of self or the avoidance of unknown future risks against the immediate reality of curing devastating genetic diseases with CRISPR, restoring movement with implants, or ending the tragic wait for organ transplants with bioprinting?
Even if those interventions do change how people feel or how future generations develop, that fundamental tension between preserving essence and improving function feels like the tightrope we'll be walking for the foreseeable future.
It is. Navigating this post-human frontier will require not just scientific brilliance, but immense wisdom, caution, and a commitment to inclusive dialogue. It's a challenge for all of us.
Thanks for listening. Until next episode.